Hey everyone, I hope you all are safe and doing good. Let's see one more lead code question. Lead code 746 Min coast climbing stairs and asked in top tech companies like Google, Amazon, Meta. What is this question? We have done climbing stairs, that question. So please watch the previous video first, then come to this video. Then you will get it easily. You are given a integer array that is coast, where coast I is the coast of ith step on the staircase. Once you pay the cost, you can either climb one or two steps. This step is important. You can either start from step with index 0 or index 1. This is important, right? You have to return minimum cost to reach the top of the floor. You are supposed to, in the previous case in climbing stairs, you found out what? Distinct ways to reach till top of the floor. But here what? Minimum cost to reach the top of the floor. You are given cost. See, cost is given 10, 15, and 20. So this is 0th index, 1 and 2, like that. Suppose this 10 cost 10, cost 15, cost 20, and this is top. This is top. One mistake generally students do is they consider this as top. That you can start from index 0, you can either start from this or this. It's up to you. And you have to reach on the top of the floor. Top of the floor means you think that let's start from 1. So you start from 1, pay the cost. Before moving further, you are here. So before jumping, you can jump 1 or you can jump 2. But before jumping, you have to pay 10 rupees. So 10 rupees you paid. Now you jump, suppose 1 step. So you reach here. And you suppose you jump 2 steps. So you reach here 20. So maybe students think that we reach 20. So it will be like top of the floor. So 10 plus 20, cost is 30. It is not top of the floor. Top of the floor is outside here. That's one statement. That's one point. Because you are given cost from 0. So 0 to n. 0 to, you can say, suppose n here is 1, 2, 3, 3. N is 3. Yes. And you are given cost for 0 and 1 and 2. So 0, 1 and 2. And n is 3. So top is 3. Here. You have to reach here. Till. Here. So out of the boundary you have to reach. That is top. Okay, one step is clear to you. I guess one point is clear to you. Next point. Now, how you will reach here? So one is, I will start from 10. Okay, let's draw this here. So see, one thing, let's start from 0. I have to reach something like this. For 0th, it's 10. For it's 15 and the cost is 25 and here is the top. So you have to reach here. You can start from here or from here, from 0th index or from 1 index. Let's start. I will start from 0. Let's start. Let's start from 0 index. So the cost is 10. I will start from 0. So the cost is 10. Or you can say, I'll start from 0 here. So the 10, 15 and 25. So I'll start from here. Suppose take a variable I, which is here. I'm going to start from here. Now I have options. I have choices. In the question, you have two choices. You can either climb 1 step or 2 step. So you have choices. Plus, you have to find out what minimum cost. So it's kind of DP sign. Choices are given and you have to find out minimization. It's a minimization problem. So optimization problem. Right? You may think that it's maybe greedy, but I'll show you that thing also. Why it's not greedy. See. I will start from here. I can take 1 step or 2 step. So when you take 1 step, so I start from 0. When you take 1 step, you will reach at index 1. If you take 2 step, you will reach at index 2. Because you need to find out, you have choices at every step. You have to take decision at every step and you have to find out minimum. So we explore every path and then we decide which is minimum. So it's kind of DP. We are not greedy that at this stage, whatever minimum, just take that. Suppose you take Suppose you are thinking, let's take, it's a greedy approach. We can solve it with greedy. Suppose we are here or here. At first, we can start from here. We can start from here. So I will take whatever the minimum. I'm greedy. I'm following greedy approach. Yes. So whatever the minimum, I will start, because in greedy we choose locally the best choice. We don't consider future and all. At that point, what is the best? I'll choose that. I don't care about past or future and just move forward. That's because I'm greedy. So minimum is 10. So I will choose 10. I will start from here. Now after 10, either you can go here, here, or here. You can take one step or two step. But before jumping, you have to pay 10 rupees. That's for sure. So you paid 10 rupees plus. Now you can go here or here. Now what is next minimum? Because I'm greedy, so I'll choose next minimum. Next minimum is 15. So I'll go here. So plus, I will go here. Now I'm here. So plus 15, because I haven't reached till top. Top is here. Here. So now I'm here. So I can go here or here. Two options you have. Yes. So one is this, two step is this. I know that if I take two step, I can reach to top. So I will take two step. I don't want to pay 25 rupees. So I'll take two step, and now it will give me answer is 25. So according to greedy, the answer is 25. According to greedy, the minimum cost you will give, or you need to pay from here to top is 25. But that's not correct answer. We know we can start from 0 or 1. So I will start from 1 index. I will start from 15. So at first I'm here, here. Now I can go here or here. I can take one jump or two step. So I'll directly take two step and I'll reach till top. So what is the cost? Only 15 rupees. 15 is minimum, or 25 is, obviously 15 is less. So that's correct path. Greedy will not give you correct answer in this case, obviously. You can think it's common sense, because I'm greedy here. Suppose right now, okay, minimum is 10, but maybe later whatever path I will choose, but later I have to pay more. So first try to explore all the paths, take future references also in mind, and then decide you have to, which is minimum. So that DP will do. So it's not greedy. We can't solve this with greedy, right? Greedy is like, if you're going somewhere on a trip, suppose from your home to some like Dehradun or some other hill station or some other destination. So at whatever cheapest on that night, you will choose that hotel. You are greedy. But DP is what? I will accordingly plan that my flight total trip is cheapest. I have to pay the total trip cheapest price. So accordingly, I will plan. I will take future, you can say references also. What can be in future? So if you have data, then only you can decide. So data means we prepare data here. In DP, we prepare data, you know. Now let's go for dynamic programming. Or for now, it's recursion. Because obviously at every step you have to decide either this or this. Either this or this. So you can make a tree kind of thing. Right? So that's recursion. Na? Okay. We start from 0. One step means we can reach to one index, or two step we can reach to 2. But obviously either you go to 1 or 2, you have to pay 10 rupees. You have to pay 10 rupees because you are here. Either you go here or here, you have to pay 10 rupees plus 10 plus 10. Now, I have two choices. I'm at 1. I'm at 1. I can take one step or two step. When I take one step, so I can reach to 2. I can reach to 2. If I take two step, I can reach to 3. Same with this. I'm at 2. I will take one step. I will reach to 3. I take two step. I will reach to 4. Okay. But whatever you take from 1 to one step or two step, you have to pay before moving, before jumping, you have to pay 15 rupees. Plus 15 plus 50. That is for sure. Right? Same. You are at here, you are at 2, means you are here. So you will take one step or two step, you have to pay 25 rupees. First pay 25, then jump. But I guess no need to pay for 4 because the top is here. So that is out of boundary. So the base cases we write. We reached because 3 is out of boundary means we reached at the top. But this is still you have to explore this path. We are still at 2 in this path. Explore it. One step, I will reach to 3. Two step, I will reach to 4. We are at 2. 2 means cost is 25. So when you jump, plus you pay 25 first and then you jump, plus 25. Now see, when you stop, what is the base condition? When, suppose that is I. So when your I becomes greater than or equal to n is 3, then we stop. Stop means we return 0. We reach, here we stop, here we stop, here also we stop because we reached, here we stop. So if I take this path from 3, so it's 25 plus 15 plus 10. It will be what? I guess 50. If I take this path, 25 same, 15 plus 10 same, 50. I have reached in this path also. If I take this path like this, 15 plus 10, 25. If I take this path, 15 plus 10, 25 plus 10, it's 35. And that's for we don't need to go here. So it's 35. It's 35. So whatever minimum out of these paths is 25. So this will give me 25. But we know this is not the answer. Because we are starting from 0th index. That's why you are getting 25. You have option. You can start from 1 as well. So let's start from first index. Let's start from 15 and 25. My I is here. I will start from here. I can take 1 step or 2 step. If I take 1 step, I will reach to 2. If I take 2 step, I will reach to 3. Yes, whatever you step you take, but first you have to pay 15 rupees and 15 rupees. Now you are at 2. Either you take 1 step or 2 step. So we reached this. We can't consider because this is the base condition. We stop here. But whatever step you take, you have to pay how many rupees? At 25, the cost of this is 25 plus 25, but just ignore it. Now see, if we take this path from 3 we reached, so if we total calculate 25 plus 15, that is 35 and 40. But to this, because we reached, so it's 15 only. It's 15. Whatever minimum, 15. So it will give me 15. So 25 is minimum or 15 is minimum? 15 is minimum. So we take this path. We start from 1 and we go directly, we jump 2 step and we reach till the end. So ultimately what you are doing, whatever minimum from this or this, we take that. This was 25, this is 15. We take minimum of these two, that is 15. That's how we write. If I write it something like this, like climb stairs. So I'll pass. So there is a method in which you are given only cost, means you are given only this array. Only this array you will be given. So we calculate here n, that is length of this array, n. It will give me n is equal to 3. Now what you do? We call from 0 and from 1 recursively, because obviously from minimum of 0 and 1 is the answer. Answer is you can say it's like minimum of from 0 or from 1, whatever you get. So on this you have to call recursively, because to get this value 25 value again we have to find out, because we can go to 1 or 2, then again 1 to 2, then again 2, 3 to 4 and like that, and when we reach to dead end we stop and then we calculate. So it's like recursively. See, sub problem says we are calculating for 2 here, again we are calculating for 2. Yes, so that is kind of sub problems. These are repeating sub problems, so we can optimize it also. So DP we can use, that's a sign. So that's why always draw, when you have choices, always draw such kind of tree so that you get a clear idea. You have repeating sub problems or not. Okay. It's a 1D DP pattern because only one parameter you are passing. So it's 1D. Right. But now, see, you call, okay, from 0 you call on 0, or on 1 you call some method, like let's call helper. We pass in this cost as well as 0, because we are calling on 0 first, plus 1 method we are calling, passing cost and 1, and whatever minimum of these two, that will be my answer. That will be my answer. I know. But how to calculate now this at 0? We are starting from 0, then we have to calculate the minimum. The minimum. So we are passing, let's suppose we are calling here helper, and here we have cost array and int I. I is 0. For now, I is 0. So we keep calling, keep moving, we keep moving. When you stop, the base case is if I is greater than equal to n, then we return simply 0. Because when you reach at the top, there is no cost here. Because once you reach here, so to find out total cost, we consider, we check that can we go back. So we do just plus this, plus this, plus this, like that. So the cost here is 0. There is no cost. So once you reach at top, return 0. Else we do what? Okay. Now see, we can go to 1 or to 2. We explore this. So whatever minimum to reach till this 1, or whatever cost to reach from 1 to top is here. Whatever cost from 2 to 3, 2 to top is here. So we take a minimum of these two. Yes, we take minimum of these two. Then only you get finally minimum here. Because see, if you go in this path, so it's, we just ignore this 25 plus 15. That is 25 plus 10, 35, and it's 40. So in this path, it's 40. In this path, it's 15. So we'll take minimum, that is 15. So we take 15. Here, 25, 25. So it will be 25. Now, 15 plus 10, 25. 25 plus 10, 35. Now again we choose minimum, that is 25. Yes, because we have to find out minimum cost. Okay. So we just find out one thing. Suppose you find out A. What we are taking, this or this? Cost at this, cost at this. So what should be the cost? Again call this helper, passing cost, and I minus, sorry, I plus 1. We will call it 1. Second time we call helper, passing the cost, and I plus 2. I plus 2. Just take one step or two steps. So I plus 1 or I plus 2. Okay. Now out of these, whatever minimum we take, B is equal to this. But that's not it. It's not that just return minimum of A or B. No. Whatever cost plus, I've told you now, if you take one step or two step, it doesn't matter. This 10 will be added. You can move from 0 only after paying 10 rupees. Okay, this will give me, because I'm calling this helper on this one, this will give me cost on this one. But I have to add this plus 10 also. So plus cost of I you have to add. Here also you have to add cost of I. That thing you need to take care. Cost of I means when I is 0, so cost of 0. Cost of 0 is 10, 10. So we add this also. Now return minimum. After whatever cost is here, that is 15 you get, 25 you get, we add 10, 10, and then return minimum of A and B. That's recursively we call. If suppose I, we are calling at 1, so I is 1. We are calling at 1, so I is 1. 1 is greater than equal to n? No. Okay. Just call helper. So we pass cost and I plus 1, that is I is 1. So we can take one step, that is 2. We can take two step, that is 3. So just call in here 2 and 3. You will get only the minimum cost from 1 to top only when you have minimum cost from 2 to 10, from 2 to 10, from 2 to 3. So just calculate on this also. This will be 3, so it will simply return 0. For I plus 2, right now it will return 0. 0 plus this cost. 0 plus this cost, 15. So this will give me 15. What this will give you? I plus 1. I plus 1 is 2. We are passing now 2. Is 2 less than equal to, 2 greater than equal to 3? And no. Again call. So for this we are calling plus again 1 plus again 2. So plus 1. If you are calling plus 1, that is 2 plus 1, that is 3. So it will return 0. It will return 0. Whenever it will return 0, we add 25 here. I plus 2 also becomes 4. That is true, greater than equal to n. It will also return 0. Then cost will be added, that is 25. And it will return minimum of a and b, that is 25, 25. Minimum is 25. So it will return 25. Okay. This 2. It is 15. Now finally, again, we are returning because it's recursive. So we are again returning 25 plus 15. It will be 40. Or 15. It will return only 0. So 0 plus 15, that is 15. So minimum is 15. That we will take 15. So I guess you get it. In this case, we are going from here to here. Right? We can start from 0 or we can start from 1. If you start from 0, then you can move to here and here. So first you have to find out from here to top, whatever the minimum cost, whatever here to here, whatever the minimum cost, and then we take a minimum from these two, and that will be the minimum cost from 0 to here. You can go right like this also. If you're not getting this, if you're not comfortable, you can go in backward direction. Suppose n is 3, so we consider something like this. This is top, so we are here. You are here. N is 3, so you are here at top. What are the ways you can reach till here? Either, because you can take only one step or two step. Either you came from this by taking one step, or you came from this by taking two step. Yes. So it's like we can write fn is equal to f of n minus 1. F of n minus 1 or f of n minus 2. And out of these, we take minimum. Out of these, we take minimum. Because I want a minimum cost. So whatever cost from here, cost is there. If you reach here, so a cost is there. Whatever minimum, I take that and I can reach to top. What about this thing? If you are at here, n minus 1, it means maybe, or steps are something like this. Let's take a bigger example. So that's n. So that's n minus 1, that's n minus 2. So either you have reached from here by taking one step or two step. Okay, fine. So we take minimum of these two. But what about this? What about like if I write f of n minus 1, it's like either you will take one step from here or two step from here to reach here. So it's like f of n minus 2. I will simply write, if I write minimum of f of n minus 2 or f of n minus 3, n minus 2 or n minus 3, like that we keep going. But it's not that simple. You have to add a little bit here. Okay, you reach here. You reach here by taking minimum of this or this. But ultimately you are not at top. You are not at top. To reach at top, either you have to take one step or two step, that is for sure. Or you will take whatever step, one or two. You have to pay the price, whatever the cost is there associated with this stair. When you pay, then only you can jump. So, right? So for this, the cost is minimum of this or this plus whatever cost of this n minus 1. That's one thing. Same for this also. It's like I can reach from here to here or from n minus 4 to here. So minimum of n minus 3 or n minus 4 plus whatever cost. Because if you are here, obviously you are not at the top. So you have to move either one step or two step. Once you pay the cost of this stair, then only you can move. So here also you will have to add this cost. Like this, we keep moving. We keep moving till we reach stair 0 and 1. That's because that's from where you can start. So that's initial point. So directly you reach till 0 and 1. That is my base case. Till then we keep moving like this. So if you have to write this in a simple statement, so it's like f of I is equal to cost of I plus minimum of f of I minus 1, f of I minus 2. Like this you can write. This cost of I also you need to add. And minimum of minus I and minus 1 or minus 2. And I will be because these are base cases, so I will be from here to n minus 1. We don't consider this n because that is top. So here the cost is 0. We consider till here. I is n minus 1. Till n minus 1 till less than n. So that's the formula here. I guess you can go from here to here, or you can go previously from here to here, from here to here. In whichever you are comfortable with, you can write down. Okay, it's up to you. Okay, so that's question 746, min coast climbing stairs, and we have to complete it. Right? Let's try this out. You are given a coast array. So you can find out length. Int n is equal to coast dot length. So you get the top of the floor where you need to reach till end. Okay. Now what we do is we just call a like helper rec. Let's name it helper rec. It's recursive method, and there we pass coast, and at first I'll call 0 and 1. So helper rec 0 and helper rec, we are passing coast and passing 1. Whatever minimum of these two, that is my answer. Okay. So I will simply return math.min. Whatever minimum out of these two, that will be my answer. I know this thing. Because I can start from 0th index or first index. So I'll find out from 0 to top, what is the path. From 1 to top, what is the path. I'll take minimum of these two. Yes. Okay, fine. Now let's define this. Helper rec. First is my coast array, and next is, let's take I. So I is 0 at first. We are calling for 0. We are calling for 1. What we do? Base case. It's recursion. So what is the base case? When we reach the top floor or greater than that. So when I becomes greater than or equal to n, there is no n. So we can simply write coast dot length here because we are not passing n. So coast dot length. We can comment out this thing. If I becomes greater than that or equal to that, then simply return 0. There is no cost at that step. You don't need to pay anything. Okay, you reached. Otherwise, what we do? We find out. Let's take two variables. A is equal to, we call for I plus 1 and I plus 2 because we can take only either one step or two step. So recursively we call helper rec passing coast on I plus 1, and second value is helper recursion coast, and I value is I plus 2. But here you need to add what? Whatever cost of that I. Right now I is 0. So to move from 0, either you take one step, that is I plus 1, or two step. You need to pay first 10 rupees in that example. So add that cost as well. Here also add cost of I plus, and then call for I plus 2. Then at last we return whatever minimum of minimum from these two values, A comma B. That's it. So at first it will give me for 0, then for 1, and out of these two values, I will return just minimum. Let's run this. But it's recursion. At every step, you have two choices. So the tree can grow exponentially. At every step, two choices. At every step, two choices. So you know now binary trees we have seen. So it's like the length, or you can say the number of recursive calls can be 2 raised to power n, exponential. So you will get here, if you submit, TLE error. It's not allowed. Time limit exceeded. You have to optimize it. So see, let's submit it and see, you get TLE error. Okay. But I guess the idea is clear to you, how you do it. Now, if you want to write, because I have started from 0, you know, from 0 and 1, and I go till top. The base case is once I reach to top, then return 0. But you can start from top as well in recursion, and you can reach till 0 and 1. 0 and 1 can be base case. So let me just quickly write down that also, if you are not getting. But first you pause the video and you write down that way yourself, that approach yourself. Okay. I hope you have done this. So in this case, what we call n, we have n. So helper rec cost, and we are passing n minus 1, n minus 2, n minus 2. And whatever minimum of these two, that will be my answer. Okay. So in this, we are passing n minus 1, n minus 2. That is, suppose I we take. And base case will be, in this case, my base case is, because I am returning back, n is 3. So minus 1, minus 2. So it can be 0 till 1. So base case is, if I is equal to 0, means from that we can start. That's initial point. So return cost of 0. And if I is equal to 1, so that is also my initial point. So return cost of 1. These are two base cases. Base cases are really important to identify when you write recursion. Otherwise we do what? Same 2. We call here same again recursively. Something like this. And we return minimum of those two. So we call helper rec passing cost, and I minus 1. It's not I plus 1. Int a is equal to, int a is equal to, but first you have to add the cost of I, then call. Same for b is equal to, let's add cost of I, then you can jump either 1 or 2. So here I minus 2, and we simply return minimum of these two values, a comma b, because we want a minimum cost. So that's the way you write this. Let's run this and see. But here also same thing, you get TLE error. Okay, first is compilation error, so semicolon is missing. Let's run this again and accept it. But you will get still TLE error because it's still recursion. If I submit, you see here TLE error, same thing. Okay, I think you can optimize it with DP. Let's see. So same thing, because we are calling here, see, for f of 2 we were calling, we have already calculated here, and again we were calling for f of 2. So we store this value. Yes, that was 25. And whenever we go here, we don't hold these. Directly use 25 from here. Right? So it's a table, or it's like a 1D array. 1D array. You can name it DP. Same. Size will be whatever n plus 1. Okay? Because there is only one variable which is changing. So we need 1D array only. So this DP of I, whatever 0, 1, 2, 3. Here we need only size 4, because n is 3. So we need 4 size, so that we can have 1, 2, 3 index. So this DP of I will represent what? The minimum cost to reach from this to top. The minimum cost to reach from this to top, that is this DP contains. Right? I think it's not tough to optimize this. Same, we take DP array, we fill it with -1, and before returning, we just store that value in this DP array, and then we return. And while checking, first we check, after the base cases we check if DP of that I is not equal to -1, directly return that value. No need to call further. No need to call further these recursive calls. Because once we have done this dp2, so while returning back, we store this dp2 here. That is minimum of these two, that is 25, 25. So here it will be 25. Now, whenever we call this, is base case true? No. Is dp of this 2 not -1? Yes, it's not -1, it's 25. So directly return 25. Don't call these two. Directly return 25. So it will drastically reduce, number of recursive call. Number of recursive call will be in polynomial, maybe 2n. So ultimately time complexity will become order of n. Okay. Why order of n? In Fibonacci series, we have discussed that thing. So it's kind of same tree. There also, there was recursion and 2 recursive calls were there. In everything we have two choices. Here also we have two choices. Same kind of tree, same logic will be there. So if you're not getting how this time complexity will be order of n, you can watch that video. How the number of recursive call will be reduced. You can watch that Fibonacci series video and you will get it. Let's quickly optimize it. Okay, so we optimize this one only. What we do is, let's take an array dp of size n plus 1 and arrays dot fill it with -1. Fill it with -1. Now you need to pass cost, then n-1, and then dp as well. So just pass here dp as well. So you're passing this. So here also you need a array parameter dp. After this base case, we check. Before calling, we check if dp of I it's not equal to -1. Then simply return whatever the value at dp of I. No need to call recursively these further. Otherwise, if it's not the case, then call recursively. And before returning these values, you have to store it in dp of I at that index and then return. So directly you can write here something like this. It will first store that value here and then return. Or if you want to write in 2 steps, you can write like dp of I is equal to this. In the next step, you write return dp of I. It's up to you. And yeah, that's done. That's how we optimize it. Let's run this and see. Compilation error. Okay, sorry. Because we are calling recursively this, so we have to pass here one more argument, that is dp, our array as well. Accepted and submitted. Now there will be no TLE error. Submitted. Okay. And for same, if you are following this approach, if you are calling for it's like for 0 and 1, not on n-1 and -2, for 0 and 1, then same thing you can do. After this base case, you can write down this condition. Before returning, just store it, and same thing. Right. Now, okay, that is top down. That is basically we are using memoization here. What if you can can you do it with bottom up approach as well? Bottom up DP approach. Like we directly fill this DP, this table, this 1D array without recursion, just iterative. Yes, that's really easy. Pause the video and you try this out. These were two base cases, I and 2, DP not equal to, if DP of I not equal to -1, we return this. Otherwise, DP of I is equal to this and we can return DP of I. So I haven't written here on the board int a is equal to this, b is equal to this, because ultimately this was same, cost I is same. So whatever this will return, I-1 and I-2, these helper method, we take minimum from this and just add cost of I and store that into that DP array and just return that. You can write down in a simple one line also, that's fine. Convert this into just don't use recursion. Just take this array like 0, 1, 2, 3. At first, -1, -1, -1, -1. We know base cases. We know DP of 0 is what? 10. So we change it to 10. DP of 1 is 15. So we change it to 15. Okay. Now we have to fill this. Have to fill. See, to fill this, we need what? Minimum from this, because we can come from 1 by taking 1 step, or we can come from 0 by taking 2 steps. So this will be whatever value here, it represents the minimum. The minimum cost to reach at stair I. Ith means at stair 2, the minimum cost. Right. So minimum of these two plus whatever cost at 2, that also we add, obviously, because that's not top. We add this. So minimum is 10 plus 25. So 25 plus 10 is 35. Fine. Let's move here. We start loop from here to here, because with these two are base conditions. So loop we will start from here till here, till 3. Okay. Now see. Okay, loop will start from here till n minus 1. So n is 3, so n minus 1 means till 2 we will go. Now at last, whatever minimum out of this or this, that we take. 15 is minimum, so that will be my answer, because with 2 step I can reach here. Okay, let's take a the second example here. See, we take a DP array. N is 10 here, n plus 1, that is 11 size. At first, at 0, simply we take, just we write, at first there is a some method here, there we are passing simply cost. We don't need any recursion here. Okay, so DP of 0, DP of 0 is equal to whatever cost of 0, and DP of 1 is equal to whatever cost at 1. So here we have 1, here we have 100. These are base cases we know. Now we run loop from 2 till top is what? 10. So till 9 we will run the loop. So we run a loop from 2 to n minus 1. Not n minus 1. Okay, because n is what? 10, that is top. So you are given values from 0 till 9. 10 will be out of boundary. So we have to run till 9 only, n minus 1. Now have to calculate this. At first I is this. So DP of 2, how you will calculate? The value at this is what? At ith index is what? Minimum cost to reach till this stair. Till this stair. So have to reach at second stair. Here we have 1, here we have 100, then we have 1, then we have 1, like that. But this and this, how to reach here? You can take 1 step from here or 2 step from here. Okay, but minimum we will take. That is 1 I will take. So I'll take 1 plus this one also. So it will become 2. Because ultimately when you jump from here 1 step or 2 step, this one you need to add. So that is cost to reach till this stair, that is 2. That's how we do. So DP2 is equal to what? Minimum of whatever cost at 1 or 0. Minimum of these two plus cost of this 2. So how to write this thing here? In general form, DP of I is equal to cost of I. Same you need to write here. The same thing. Rather than recursion, we just use here simple a DP array. Cost of this plus minimum of DP of I minus 1 and DP of I minus 2. That's what you write. At last, what you return? It's not that simply return DP of n. No. Because n is 10. So at 10, obviously it will be minus 1. No, that's not a case. That's top. What you need to return? See. You need to return at last whatever minimum from this or this. Because if you have to reach here, so take minimum, that is 1 plus 1. It will be 2. If you have to reach here, take minimum from these two, that is 2. 2 plus At 3 we have one value, so 2 plus 1, that is 3. It will be 3. Here, minimum of these two, 2 or 3, 2 is minimum. At 4, 0, let's write down 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is my cost array. So minimum is 2, cost of 4 is 1. 2 plus 1, that is 3. At 5, minimum from these two, that is 3, 3. So 3 is minimum. At 5, we have 100, so it will become 103. At 6, whatever minimum from these two, that is 3. And at 6, we have 1, so it will become 4. How to reach 7? Minimum of these two will take cost, so it's 4. 4 plus 1, that is 5. 8, minimum of these two, that is 4. 4 plus 100, that is 104. Now at 9, minimum of these two, that is 5. 5 plus 1, that is 6. And we stop because we run the loop from here to here. Now, what is the minimum cost to reach at the top? That is here. So we can go either from this or this. One step from 9 or two step from 8. How to reach top? Just one step from 9 or two step from 2. Yes, but we take minimum from these two. So just return math.min dp of what? Right now I becomes 10. So that's why we'll be out of the loop. So I minus 1 and I minus 2. That's what you need to return. That's how you can convert that into just bottom up approach, DP approach. Okay, that's it. One loop only from 2 to n minus 1. So we are scanning this only once. So it's order of n. We are scanning this and we are scanning this once. So it's order of n. Time complexity. Space complexity extra, we are taking what? This DP array. So space complexity is also order of n. Time complexity is also order of n for this. Okay. Pause the video and you write it out. Okay. So what we do is let's comment out this recursive method. We take DP array, we fill it with -1 and just comment out this. Just write down DP of 0 is equal to whatever cost of 0 and DP of 1 we fill with cost of whatever at 1. Now we run a loop where I will run from 2 to I less than n and I plus plus, not less than equal to n, less than n. Now we fill DP of I is equal to cost at I plus minimum of math.min whatever previous two values I minus 1 and I minus 2. Simple. And at last you will simply return math.min dp of I minus 1 or dp of I minus 2. So run this and see. Variable I cannot find variable I. Okay, sorry, because it's not I minus 1. My mistake, it's n minus 1. N minus 1 and n minus 2. On the board also, it was not I minus 1, it's n minus 1. Because obviously I is within this loop only. Okay, we have n. N is the top. So we filled the complete array. Now n becomes the top. So n minus 1, n minus 2. We can reach with one step or two step. So whatever minimum, we take that. Let's run this. Accepted every case and we can submit. So that's how we do it. Right? Yeah, one more thing. You don't have to fill actually with this -1. Just keep it as it is. So everywhere it's 0, 0, 0, 0. Okay. So like this also you can submit. If I run this and accepted every case and you can submit it. So that's quite fast because we don't have to fill it. So that was unnecessary. But in this case, you have to fill. See, I'll show you. If I just comment out this as well. And let's go for the recursive approach. Uncomment this n minus 1. And let's uncomment this also. Having two base cases 0 and 1. If it's, suppose I'm not filling it with -1. So initially everywhere it's 0, 0, 0. So I will check if DP not equal to 0, because there is no -1. So initially I think that if there is nothing, so I'll consider 0. So if DP is not equal to 0, then return that value. If it is 0, means we haven't computed that value yet. Means that in this approach, in recursive approach, this will not work. If I run this will give wrong result for some test cases. So these test cases are passed, accepted, both case 1 and 2. But when I submit it, you see the difference here. See, time limit exceeded. When the input is 0, 0, 0, 0, 0 and 1, 1, only here we have 1, 1. So in that case, you are using memoization in your, you can say, context. You are using it, that I'm using DP and all. So it's, I have optimized recursion. So but still you are getting time limit exceeded because the input is this 0, 0, 0, and you haven't filled your array with -1. So in array also, everywhere in DP array 0, 0, 0, 0, 0. So whenever it will consider that if DP is not equal to 0, then only we return that thing. If it is 0, then it assume that it is not computed. So it will keep going, keep going, keep going. We are not able to use the already computed subproblems values, the result. That's one thing. So in this case, you must have to fill it with -1. And here you need to check if DP not equal to -1, then return this, and otherwise this. So let me show you now. Now you will not get this time limit exceeded error. Let's submit. Yes, that's it. We're done. So these are few, points you need to take care. But why in this case this works? You can just dry run that and you will get it. So dry run all the approaches, all the codes with different examples, and you will get it. Okay. But still, now we can optimize it more in terms of space complexity. Because when you have to find out the next, when you are, let me just comment out this and then comment this one, this bottom up approach. Let's comment out this recursive method. It means when we are, filling this DP array, we just consider previous two values. Just consider previous two values. So we just need two values and one is current value. Three variables we need. You can optimize it. We have already done this in Fibonacci series. So I guess you can do it. Pause the video and you try this out. Don't take this DP array. Comment out this. Just take only two variables. That's it. So we have done this in this Fibonacci series. I will take the same thing. Previous one, previous two, int current, and let me just Control C and I'll paste it here. Pre1 is DP0, pre1 is DP1, and we take int current is equal to or nothing. Run the loop from here to here and just comment out this. There is no DP array here. We calculate my current is equal to cost of I plus math dot minimum from previous two values. Previous two values are in pre1 in this variable and pre2. So directly you can write it. After that you have to change it, previous values. Now just Control V. I'll just remove this. I'll change first my previous one is equal to previous two, and now my previous two becomes my current, and we repeat the same process. And then at last what you will return? Minimum of previous one or previous two, that you will return. So at last you will simply return pre1 comma pre2, minimum of these two. Simple as this. Let's run this. Cannot find symbol here. DP. Okay, sorry. Previous one is equal to, it's not DP0, it's cost 0 and cost array, because we have now. From here we fetch values. Cost 0 and cost 1. So accept it every case and submit it. So yeah, it beats 100%. In memory also it beats 94% almost. So space complexity is also less. It's constant. Just taking, we are taking 2 3 variables, so it's constant. If you're not getting it, I have discussed this also completely in my Fibonacci series, that example, or you will dry run this. Just dry run this code and you will get it easily. Okay. So I think we did this problem with 4 approaches. First was normal recursion, right? In this case, time complexity was exponential, space complexity was also order of n. Second was with that top down approach, means with memoization, recursion plus memoization, top down DP. In that case, it's order of n, space complexity, time complexity is also order of n. Third was we did this with bottom up DP. In that case, also time and space complexity both are order of n. But then fourth, we have optimized space optimization. In that case, time complexity order of 1 n, but space complexity was order of 1 itself, constant. So I guess you get everything about this problem. You try this out. That's it for this lecture. I'll see you in the next lecture. One more DP problem. Till then, bye bye. Take care.